Okay, so let's start by looking at some proofs that we already did. It's just, I don't know if we were really calling them examples of proofs. But now we are going to look at them not as our attempt to prove something, but as an illustration of how would you prove things like that in general. So, first of all, when we are talking about existential quantifiers and formulas that start with existential quantifier, we kept saying that it's very easy to prove things that start with existential quantifier, usually, because the only thing that we need to do is to find some value of that variable, that quantified variable that makes the formula true. It's enough to find a witness. So let's do an example. Suppose we want to prove that theorem, let's call it theorem because it will be hopefully a true statement. And our theorem will say that there exists a natural number that's both even and prime. Here is the whole proof. Let's take number 2. 2 is even, yep. 2 is prime, sure. Therefore, it's true that 2 is even and 2 is prime. That's great. We found a witness for that x under the quantifier, and we are done. This kind of proof is often called constructive proofs, and those are the proofs that are loved by computer scientists because when we are proving something, oftentimes not only we want to show that something is true, but we want to know how to find the thing that makes it true. We want to give actual, tangible, solid object that would witness that quantifier. And this is a kind of proof where we can achieve it. So again, we already mentioned it before, but the other side of witnesses is counterexamples. To prove that something exists is the same as proving that the opposite is not true anywhere. Similarly, to disprove a statement, it's enough to give a counterexample. It's enough to give a scenario where the statement is false. So here is an example. Suppose we have a statement that says no matter what A and B are, if A implies B, then B implies A. You look at it and say, well, wait a moment. This is not quite right, because if I take A to be true and B to be false, so that's my scenario, then A implies B will be, well, true cannot imply false, so that's false. But the right side, B imply A, will be true. Here, we disproved that no matter what A and B are, if A implies B, B implies A, the other way around, by just presenting one scenario, A being true and B being false, for which this actually doesn't work. So disproving a statement is the same as proving its negation. That is, I could state it as there are A and B such that A implies B is not the same truth value as B implies A. And here is an example of that. So let's look at a little bit more involved counterexamples. So in this case, implicitly we were talking about all possible formulas A and B. In general, we may be talking about all possible, well, all sorts of things. So for example, we could say no matter what the predicate P of x, y is, no matter what domain S its inputs x and y are defined on, if for every x in S there exists y in S such that P of x, y, then it must hold that there exists y in S such that for all x in S, P of x, y. Well, your first reaction may be, wait a moment, didn't we just do something like that on Valentine's Day? The first one has a structure of everybody loves somebody, and the second one has a structure of somebody is loved by everybody, but normal people, general people is one thing, and Elvis is something completely different. That would already be a good counterexample. But let's just, for the sake of it, construct a counterexample which is a little smaller, a little bit more mathematical, and doesn't have the controversy of whether everybody really does like Elvis. So let's take S to be some small set, enough that we could look at all the possibilities. And let's define P on S to be like this. P of 0, 0 and P of 1, 1 will be true, and P of 0, 1 and P of 1, 0 will be false. Another way of saying it is let P be true whenever x is equal to y. So we are constructing counterexample. Our statement said no matter what the predicate is and no matter what the domain is, something is true. But we are saying, no, wait a minute, I can give you a predicate and a domain for which the thing that you're claiming always true is actually not. And here is a domain, 0, 1, and here is a predicate, x equals y. Now you could check that for every x there exists y, p of xy is true, but exists y for all x, p of xy is false. And because our domain is so small, we could actually use the trick of writing out all the possibilities in order to check whether the statement is true or false. Okay, so how do we prove universal statements? Well, one possibility is to prove that it holds in every single possible scenario. So no matter what A and B are, well, when we are talking about A and B being true, false, not B implies not A is equivalent to A implies B. You could look at the truth table of both of them, check that those truth tables are the same, and conclude that that equivalence is indeed true. But you know what? Here we are only talking about 4 possibilities, because each of them can only take the value true, false. But there can be way too many scenarios to consider. If we are talking about numbers, for example, we really don't want to look at every possible number. There are infinitely many of them, there's way too much. So how do we prove something like for every integer there is a larger integer which is prime? How do we show that for any real numbers there is a real number between them? For that, we will develop some more reasoning techniques, some more rules of logic, rules of inference, and then we will show how we could use that knowledge of logic in order to prove statements like that. So what we will want to do is we'll start with, well, kind of start with axioms and eventually get to showing the statement like that is true. So before we go that, consider the following puzzle. Let's define the set S to be all natural numbers that are both even and odd. Now, is this true or is it false? That for every x in a set S, x does not divide x squared. Do you think this statement is true? If so, how would you prove it? Do you think the statement is false? If so, how would you disprove it? So think about it for next time.